Maximum likelihood estimates have some very nice properties, and the purpose of this subsection here is to discuss how we can work with these maximum likelihood estimates. First of all, there's something that's called the invariance property of maximum likelihood estimators. And what this basically says is this, that if I have the MLE of some general parameter, let's call it theta, but what I really want is the MLE of some function of it, let's say log of theta, all I need to do is simply plug in what theta hat is into this function. So thus the MLE of log of theta is log of theta hat. A very nice, easy property to work with. We saw an example kind of like this before, where if you remember with respect to the normal distribution, we found sigma hat, the maximum likelihood estimate of sigma, that standard deviation parameter for the normal distribution, and then the MLE then for the variance parameter is sigma hat squared. Another example where this can be useful is in statistics, there's a measure often referred to as the coefficient of variation, which is simply sigma divided by mu. And what this gives you is it's a measure of variability per mean unit. This, for example, is used with respect to finance, where a coefficient of variation is small indicates you have, let's say, a lower risk investment per mean return that you get from your investment. And a higher coefficient of variation means you have more risk. So the coefficient of variation is sigma divided by mu. If you have, with respect to some probability distribution, the corresponding maximum likelihood estimates, so you get sigma hat and mu hat, then the MLE for this coefficient of variation is sigma hat divided by mu hat. Okay. Next, we're going to talk about a probability distribution here with respect to maximum likelihood. Now, just some terminology, and this is maybe perhaps being a little picky, and I haven't necessarily always used or always been this picky with respect to how I phrase some stuff, because in the end it's not that big of a deal, but I do want to mention it. So maximum likelihood estimate is the actual calculated value based upon a sample. In other words, it's using the little y's. Okay? Now, as you might expect, the maximum likelihood estimate, the actual computed value is going to vary from one sample to the next. And so therefore, we can think of then these quantities, these maximum likelihood estimates, essentially as actually a random variable. In the random variable version of a maximum likelihood estimate, let's say, y bar is equal to the sum of the capital Y sub i's times 1 over n. This random variable version is often referred to as the maximum likelihood estimator. So both can use the acronym of MLE, but there is a small difference there. One's the random variable version, one's then the actual computed value, the maximum likelihood estimate. And I just want to mention this because outside this class, sometimes you'll run into some people who will be very big sticklers on getting the terminology right. So then with respect to our field goal kicking example, the maximum likelihood estimate was the sum of the little y sub i's divided by n. Then the maximum likelihood estimator for pi, then we could denote it as, let's say, a capital pi with a hat on top of it. This capital pi is not related to the product notation. And this capital pi sub hat then would be the sum of the capital Y's divided by n. Now, one reason why I'm making a big deal about this, or I wouldn't say a big deal, one reason why I'm bringing this up, is because a maximum likelihood estimator is a random variable. And so random variables have corresponding probability distributions. And a very, very, very important general property of maximum likelihood estimators is they can be treated as normal random variables for a large sample. with a mean equal to the parameter that it's trying to estimate, and a variance computed from the second derivative of the log likelihood function. So why is this important to have an idea of what the probability distribution is for a maximum likelihood estimator? Well, think back to how when we've had probability distributions for statistics in the past. We have an idea, for example, when we were just looking at, let's say, the sample mean itself, when we weren't necessarily saying what the underlying distribution is for the y's, we used the central limit theorem, and we said that y bar had an approximate normal distribution for a large sample. And because of that, then, that allowed us to make inferences with a certain level of accuracy from the sample to the population by using confidence intervals, by doing hypothesis tests. Well, the same thing now occurs here because these maximum likelihood estimators have a corresponding probability distribution that we can work with. Okay, so let's talk more about how to find this variance. So let's say, just to be general, we have a parameter theta, and it's the only parameter of interest. We have a random sample y1 through yn, and a population is characterized by a PDF f of y. So inside of f of y, you're going to see this theta parameter someplace. Now, for a large sample, the random variable version of the MLE, let's call it a capital theta hat, has an approximate normal distribution, then with a mean of theta and a variance that's equal to this. Okay, so there's some components here. Obviously, we have a negative out in front of it, but we also have this e here. This e corresponds to taking an expected value, like what we've seen previously. And here's my log likelihood function. So it's a function of theta given my data. But notice here, now I'm using the capital Y's. And this expected value is going to be taken with respect to the Y's. That's why I have the capital versions there. And what I'm going to do with this log likelihood function then is I'm going to take the second derivative of it with respect to theta. So I do that, and notice I also have a -1 out here, so it means I'm going to invert it. Okay, now this result holds true under very general conditions. There are some particular cases where it won't work very well. For example, let's say that this parameter theta ends up being a corresponding value such that it defines the range that your random variables are defined upon. Okay, so now that I have this normal distribution result, then I can find then the 1 minus alpha times 100% confidence interval for theta. So how do I do that? I set up then again an approximate pivotal statistic. Like this. We've done this before. I can work with then the probability that negative z sub alpha divided by 2 is less than this z right there. It's less than z of alpha divided by 2. This is approximately 1 minus alpha. Then I do some algebra, so I only have theta in the middle, and then I get my corresponding confidence interval. Let me do some erasing here. Oops. Just erase it this way. So, theta hat minus a value from this standard normal, this quantile, times the square root of the variance of theta hat. Notice I have also a little hat on top of there. I'll explain that in a second. That's the lower bound. The upper bound is exactly the same, but now I put a plus there instead of having a minus. Okay, so this variance of theta hat here see if I can do that. Still can't do some erasing. Let me do it this way instead. So this variance here will be a function, most likely, it doesn't have to be, but most likely will be a function of theta itself. So that causes us some problems because we're not actually going to be able to compute the variance because it's a function of the parameter that we're trying to estimate. So what can we do? How about wherever you see the parameter of interest theta, you replace it with its corresponding estimate, theta hat. And so that's what this notation here then represents, that now we're actually using the estimated variance of theta hat in there. And so this little notation over here says, let's evaluate this expression here, where wherever you see a theta, plug in a theta hat. And so now I can actually compute this corresponding confidence interval because it will only be functions of sampled values. So again, when I have a hat on top of the variance, that means it's the estimated variance. Wherever you see a parameter, you stick in its corresponding parameter estimate. These types of confidence intervals are referred to as walled confidence intervals. Now, again, this normal distribution result works for large samples. Often people will refer to this as asymptotically this works, meaning that as n goes to infinity, I do have this normal distribution. So people will often refer to this property working with the normal distribution as the asymptotic normality of maximum likelihood estimators. Now, what if there's more than one parameter of interest? Well, you can do the same thing to find then the variance. You work with that second partial derivative of, let's say, theta 1, and also the second partial derivative with respect to theta 2. But now you also have covariances that you have to work with too. So if I have two parameters, theta 1 and theta 2, if I'm going to find the covariance of this capital theta hat 1 and capital theta hat 2, what do? I take the second partial derivative, where the first time I take it with respect to theta 1, second time with respect to theta 2. Actually, it doesn't matter what order you do it in, you'll get the same answer. And the rest of them in this expression is exactly as what we had above. So that's how you can work with this. So you have variances and covariances now, since you have more than one random variable. You have more than one estimator, you have more than one statistic. So let's take a look at how we can do some of this. We're going to go back to the field goal kicking example. So we found the likelihood function before. We found the first derivative with respect to pi before. And now we can find then the second derivative with respect to pi as well. So the estimated variance of pi hat then can be found by taking that second derivative of the log likelihood function with respect to pi. We plug it in to that expression for the expected value. Then what I can do with this expected value, let's say we just work with that first. What I can do is do some algebra. So I find a common denominator for these two fractions, do a little multiplication, do some simplification, and then I get to this part here. Okay. Now we're going to use the expected value. And remember, when we've worked with expected values before, that I can take the expected value through a sum. Also, I can factor out constants from that expected value. So once I do that, then I get this corresponding result. The expected value of y sub I, well, that's simply pi. So I can plug that in wherever I see that. And again, I got some more algebra that I can do. And my expected value ends up being n over pi times 1 minus pi. Thus, then, the variance, the estimated variance of pi hat, my random variable, then is I invert that n over pi times 1 minus pi. And then wherever I see a pi, I put in the corresponding maximum likelihood estimate. So now I have a pi hat in there, and here is my variance. Now, let's say I were to do this in Sage. What can I do? To do the second derivative, well, you just enclose your first derivative within parentheses and use the diff function again. Unfortunately, it doesn't really simplify the final result very well, though. Now, we've worked with a walled confidence interval before. When we were looking at the section of how to do inferences for a population proportion, we first looked at a walled confidence interval for pi. Where did this come from? It comes from this, from using the variance that we just derived, from using the normality result. It all came from this expression. Now, one thing that we found, though, let me take a look at my notes here. Now, one thing, though, that we talked about was that this walled confidence interval often doesn't work well. And partially that is due to the fact that, well, y itself has a discrete probability distribution, and we're using a continuous probability distribution, the normal distribution here with it. That's one reason. But in general, well, this result with walled confidence intervals is great. We can use it with any kind of maximum likelihood estimator. Often walled confidence intervals need large sample sizes to work well. Again, what do I mean by work well? We've talked about this before. I'm talking about with respect to the coverage, in terms of how often is the parameter of interest actually within the bounds of the corresponding confidence interval. So just be careful here with these walled confidence intervals. Make sure you do have a large sample size before you actually use it. So with that, then, that concludes in this particular section.